Oh yeah. Okay. So example 9 is my absolute second favorite. No, it's my favorite question in related rates. My second favorite is the shenanigans happening with the ladder. But this one is my favorite because it's a biopic essentially. It's pulled from the headlines that are my life or were my life. I guess it's still a part of me. A cherry flavored raspa de snow cone, is leaking from its paper cone at a rate of 2 cubic inches per minute. The paper cone's top radius is 2 inches and it's 5 inches tall. When the depth of the melted cherry raspa mixture is 3 inches, how fast is the radius of the raspa changing? Okay, so I did grow up in the Rio Grande Valley. I was born in McAllen and I lived in Edinburgh and lived in Westlaco. And we'd stop every day after school, and for a quarter, 25 cents, we'd get ourselves a raspa that looked pretty much like that. That is like the cheapest container you can put a raspa in. Those are the cups you find on the side of those water machines that are disposable, right? But yeah, for a quarter, we took it. We took it. And now you go to that place out on the loop there, where they serve raspas in like fancy cups, and they're like $8. What's it called? Bahama Bucks. Yeah, 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 yeah. So anyway, this is like inchoate Bahama Bucks. What does inchoate mean? Well, it's the word of the day. It means rudimentary, primitive, raw, early stages. Okay. So I'd get one of these, and one day I'd get a cherry, the other day I'd get a banana. Some days I just say put a squirt of everything in there, And of course, invariably, what happened is the bottom got soggy, like right away. The bottom got soggy, and so it would start dripping. It would start dripping, and I'm sitting in Miss Garza's car because I carpooled with her son David. She picked us up every day in her Volvo and took us home. And we'd stop and get the raspa. Eat it. No, 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 no. Dr. Garza's wife from the valley. You don't know her.
She's from the valley. Oh my gosh.
It's not the same one. I've already talked to that Garza. Yeah. All right. Anyway,
I've only met one.
it started leaking. So here's what we do in a related rate problem, right? If there's not already a picture drawn, we draw a picture because it helps us orient ourselves, but it also labels our variables. So let's go ahead and do that. In the loosest sense of the word rigid, this cone is a right circular cone, and it's rigid, meaning its dimensions don't change. All right. It tells us what the dimensions are. The paper cone's radius is 2. So this right here is 2. Do I want to call that R or 2? How do I know? If it doesn't change, we don't call it a variable, because variables vary, constants don't. I'm calling that a 2, not an R. Very good. Thank you. Just redeemed yourself. And the height is 5. Good. This is 5. Okay. That's the dimensions. Now, what is the variable? After I eat it down off the top, let's say that I have this much fluid. I've eaten everything above this line right here. And now I have, you can shade this. Notability makes this really nice, because you can shade this right here, kind of see inside there. The radius of the slush mixture is this. I'm going to call that R. And the height or the depth of the slush mixture, I'm going to call H or D, whatever you want. Okay. But that's what's changing, right? Now, assuming I'm not eating any more out of it, I'm just sitting there watching it drip onto my clothes. I'm sitting down, I'm holding it over, it drips all over my clothes, right? But I'm collecting data for a math problem later in life. So it's leaking out. The radius as it leaks out should be doing what? Getting smaller, decreasing, right? And the height or the depth of the slush mixture should also be decreasing. Okay, good. So those should be negative quantities. All right, so if this is the leaking part, once we have our variables, we need to go through and assign rates to every one of our variables now, okay? Let's see what we can do. Cherry flavored, is that important? Cherry, no. Let's see. The paper cone, okay, got it. At a rate of 2 cubic inches per minute. That's important. What does cubic inches measure? Volume, and we know it's related rates because it's per time. So the rate of change of volume, how are we gonna, let's use V for volume. And I'm going to call this then the rate of change of volume with respect to time. Okay. And it's leaking at a rate of 2 cubic inches per minute. 2 cubic inches per minute. Remember, perhaps the most important part here now is not just to call it dVdt, the rate of change of volume with respect to time, but to assign it the correct plus or minus. Is this plus or minus in this problem? Minus, because the volume of the slush is decreasing. Okay. We're talking about how it's leaving the cone. So that's a negative quantity. So it's -2. All right. Now, what is it I'm trying to find? Let's look at part A. When the depth of the cherry raspa mixture is 3 inches. So that's your snapshot moment. Snapshot moment. When the depth is 3 inches. So for me, that's when H is equal to 3. And I make it kind of a big camera. Because when H is 3, I might need to know at that same instant what V is or what R is or something else. Okay. But that's my instantaneous. I took a picture right there. Or David did. David took a picture of me collecting data for you back in the day. At that moment in time, how fast part A is the radius changing? So let's do part A. I give myself a target. I want to know how fast the radius is changing with respect to time. So I'm looking for dr dt equals question mark. I haven't done any calculus yet. All I'm doing is drawing pictures, defining variables, labeling rates with the correct sign, identifying my snapshot moment, and giving myself a target, right? That's all part of the setup. Now, here's why it's called related rates. Ultimately, I would like to relate dr dt to dv dt, ultimately, right? But before I can relate their rates, I need to relate their quantities. So that's where your ingenuity comes in. In a right circular cone, how can I relate the radius to the volume? Well, you have to memorize this. Memorize. Here is the formula for the volume of a right circular cone. It's 1/3 pi r cubed, or you could say pi thirds. I'm sorry, r squared h. My bad. R squared h. R squared h. I was getting kind of cylindery there. R squared h. So really, it's kind of like a right circular cylinder, which is pi r squared h. Pi r squared is the top circle, h is the height, but it's 1/3 of that. You get rid of 2/3 of the material, and you're left with 1/3 of the cylinder. All right, so I think the second version is the easiest one to memorize. Now notice that gives us the volume of the cylinder in terms of R and H, which is fine. This is not an optimization problem. I don't need to get V as strictly a function of R or strictly as a function of H. I can leave it in terms of those two variables, okay? So now that I have this is my quote unquote position equation. I want to find the rate equation. Now there's two options here. Option one is just to go for it, okay? Here's what it would look like. The derivative with respect to t colon. We always take the derivative with respect to time. There's no t in our equation up there, is there? So there's 3 variables. They're all going to get a d variable dt. All right, what would be the derivative of the left side? The derivative of v with respect to t is just dv dt. Got it. But notice on the right-hand side, I'm going to have to use the product rule, aren't I? And I'm going to associate pi thirds with the r squared. So it's going to be 2 times pi thirds. So 2 pi thirds r to the first times the chain rule dr dt. That's the derivative of the first times the second goes along for the ride. Plus the first goes along for the ride, pi thirds r squared times the derivative of h, which is 1, times the chain rule dh dt. Now this equation is fine. This is our rate equation. Or if you want, you can call it the velocity of the volumes change. But look at how many unknowns I have in here. I have dv dt, r, dr dt, h, there's r again, and dh dt. So I have 1, 2, 3, 4, 5 different unknowns. If dr dt is my target, then that's the only one that I'm allowed not to know. So in order to do it this way, I have to know what dv dt is at the moment. Do I? Yeah, I got it. It's -2. I need to know what r is at the moment. Do I know what r is at the moment? Snapshot moment? No, I don't. I only have h at the moment. Okay, so I need the, whoa, get over here, Raspa. I need to know this at the moment. And do I know dHdt? I don't know that. So I need to know two things. So crap, where in the heck are we going to go get those two things? Well, sometimes we can go straight back up to the position equation, like in the ladder problem, where you had the two sides and you just needed the hypotenuse. But in order to use the position equation, I need to know the volume and the height to find the radius. And I don't know the volume at that moment. So I'm kind of in a quandary here. So here is the essence of every cone problem. There is a secondary equation that you always have access to that relates the radius to the height. Okay, so come back over here. And if there's a golden color, like Harry would sing, golden, golden, as I open my eyes, hoping for a raspadillo. Okay, the golden kernel, nugget, whatever. I want to relate R to H. I want to relate R to H. Now, here's how you're going to do it every single time. Look at this. If you look at this right here, and you look at this right here, those are what to each other? Those two triangles? Corresponding was okay. They're proportional to each other, so they're similar. Yeah, similar triangles. Similar triangles. Okay. Yes, you could say 5 is to 2. That's the big height is to the big radius, as little h is to little r. You could do it that way, or you could do corresponding. You could say 5 is to h as 2 is to r. Either way. It doesn't matter which way you do it because the cross products are the same. If you cross multiply both sides, look what you'll get. You'll get 5r equals 2h. And over here, you get the same thing. 5r equals 2h. Your cross products are the same. Now let's simplify that. I'll use this little column right here. If I want to solve that for r, all I got to do is divide both sides by 5. So r is 2/5 of h. Or if I need it the other way around, h is, multiply both sides by the reciprocal, 5/2 of r. That is right there the distilled auxiliary, secondary, whatever you want to call it, relation. Because not only does this relate the radius to the height at any given moment, but if I needed to, I could take the derivative of both sides of this as well. Watch, I'll use this one here. The derivative with respect to t is dh dt equals 5/2 times dr dt. So not only does it allow you to relate their quantities to each other, it allows you to relate their rates to each other. So believe it or not, if I needed r at the moment, I can find it. If I need r, let's just plug into the top one here because I know h, right? So let's see. When h is 3, r is 2/5 of 3, which is what? 6/5. Yeah. And if I needed to know, what else did I need? I needed to know dh dt. At that moment, dh dt is, let's use this one. It's 5/2 of dr dt. What was dr dt? Do we know what that is? Oh, no, that's what we're trying to find. So what I can do is I can get rid of the dh dt and replace it with 5/2 dr dt. And then I can combine like terms. You know what I mean? So now I'll have 5/2. So here's what this would look like. I would have to replace dh dt with the 5/2 dr dt and then combine these two terms. Okay, now that's going to work. Yes, I have all the information now, but yucky, yucky, gross, gross. It'll work. But here's the deal. If you can find that secondary relation between the radius and the height in the beginning, why not, an ounce of prevention is worth a pound of cure. Let's substitute it in before we take the derivative. Option 2. Now, what we're going to do here is we're going to make the volume either a function of R, if we need that, or we're going to make the volume a function of H, if we need that. So kind of like what we did with optimization, where we had that secondary equation, we solved it for one of the variables and we plugged it into the other. How do I know if I want to keep R around or keep H around? Does it have anything to do with what we're given? Not necessarily, because I can find whatever I'm lacking. So I could be given R and I need H and vice versa. How do I know which one to keep? It depends on my what? My target. Yeah, that's why that's important. I need to find dr dt. So I need R to stay in my equation. So I'm going to go this route, which means I want to get rid of H. So if I want to get rid of H, come up here, I'm going to use this second one right here. Before I take the derivative, I'm going to replace H in the generic formula with 5/2 R. So here's what that's going to look like. We're going to get volume is pi thirds R squared times H, which is 5/2 R. Okay. And again, if I needed the other one, I would plug in 2/5 H for R and carefully square it to get 4/25 H squared. So you could be able to do it either way. Now I want to combine these. I'm not squaring anything, so I can just say, oh, this is going to be 5 pi 6 times R cubed. Now that's a pretty slick formula, right? It's not the formula for the volume of any cone, but it is the formula for the volume of this specific cone with that relation between R and H. And notice what I've done. I've taken out the H, so I won't need to know H at the moment, and I won't need to know dH dt at the moment. All I'm going to need is dV dt, R, and dr dt. Now let's take the derivative. We're going to get the derivative of V with respect to t equals multiply, and the 3/6 divides out, so you get 5 pi halves. 3/6 becomes a half, or 15/6 simplifies to 5/2 R squared times dr dt. So here's the rate equation that's much easier to use. I didn't have to use the product rule. Not only do I need to know fewer things, I don't have to differentiate as difficultly. Now, when we're plugging in, since it's not solved for dr dt. You don't have to solve this for dr dt and then plug in. It's easier if you plug in and then solve. So what I'm going to say here then is when, all you got to do is reference the moment in time. And I'll use the one they gave me. When H is 3, okay? When H equals 3 colon, and now I plug in everything I know. dV dt is -2. 5 pi halves is 5 pi halves. If we hadn't found the radius yet, I would go off to the side and find the radius. What is the radius? We know it's 6/5 now, right? So I'll plug that in. So you could find that on an as needed to know basis times dr dt, which is what we're okay not knowing. See, and now we can solve for dr dt. So now it's just carefully executing the math. 6 squared is 36. That's 25ths times dr dt. I'm going to simplify before I get rid of it. So 5 goes into itself once. It goes into 25 5 times. Have you ever done that on your paper like that? You cross it out, and that's fine. As long as we can see what's underneath there. 2 goes into itself once, goes into 36 18 times. So this right side now becomes 18 pi. Don't forget the pi that's hanging out there. 5ths times dr dt. And now all I got to do to solve for dr dt is multiply both sides by the reciprocal of 18 pi 5ths, which is 5/18 pi. And again, if you want to show that, because there's a lot at stake here, you can make careless mistakes quite easily. 15/18 pi. We now get -2. So I can divide this out over here now that I've shown that. -2 goes into itself -1 times, and it goes into 18 9 times. So I end up with -5 over 9 pi. Wow. A lot easier, still pretty technical, but a lot easier than using the product rule. So now I just need to put the units on it, since that's what I was looking for. And now I can return up here and say, okay, we're measuring length in inches and we're measuring time in what? Minutes, right? So this is going to be units of R. So this would be inches per minute. And now on a free response, you might ask to write a sentence explaining what this means in terms of the radius of the Raspa slush. So this is the cold yam activity you did. When H equals 3 inches, make sure you have units there, comma. All you have to do is say R is whating? Decreasing by, and then you write the number 5 over 9 pi, the positive version of the number, inches, and then we write out the word per minute. Not a very satisfying answer, but you could figure out what 5 divided by 9 pi is. Really small number, right? It's taking a while to drip out completely onto my shirt, pants, whatever. Okay. And that right there is the essence of every cone problem. You have to find some way to relate the radius to the height. And a lot of times it is similar triangles. The problem I skipped up above is a sand pile, and it basically tells you the base diameter is always twice the height. So it tells us, well, let's think what that would look like. If the base diameter is twice the height, the diameter is twice the height. So what would that mean? The diameter is equal to what in terms of R? 2R. So I'll just replace D equals 2H with 2R equals 2H. And now if I divide through by 2, I get R equals 2 divided by 2. I get R equals H. Well, I'll be a monkey's uncle. In this problem, they're the same. They're the same. So R equals H and H equals R, and dRdH equals dH dt. I'm sorry, dRdt equals dH dt. So there's always some way to relate it. If it's not given to you like that, it's similar triangles. All right. Now it's just a matter of completing the rest of the problem. Okay. Let's look at part B. How fast is the raspa melting? How fast is the raspa melt leaking onto Nino Corpi's school clothes? Well, here's what we're going to be doing, right? This is a negative number, but imagine me, and I'm not an artist, but imagine me, and I know you're going to be like, really? I didn't know that. Imagine me sitting here, right? And I've got my purple Panther shirt on for Weslaco, Texas. And then there I am. I got a purple head, and my eyes are wide, and I have a little sprig of hair, right? And I'm holding this in my hand, right? My fingers are coming around it, and then this one is just like I don't know what this one's doing. Not shooting the bird, shooting the number one. Yes, I don't know. Yeah, so there it is. How fast is it leaking onto my clothes if I'm not eating anything out of it? How fast is it leaking onto my clothes? 2 cubic inches per minute. Very good. The rate at which it comes out is a negative number because the volume in the cone is decreasing, but it's accumulating on my clothes. I'll call that D closed dt, dc dt, at positive 2 cubic inches per minute. Okay, it's a direct exchange. It's negative in one context because it's going out of it, and it's positive in the other context because it's going onto it. Now I can't use V again there, can I? So I use C for clothes. All right. It's a lot faster, but it is a rate of change of volume. So that would answer that question. All right. Now here's the thing. We got smart. If Nino Corpi has a small cylindrical cup with a 2-inch diameter beneath the leaking raspa, at this moment, how fast is the height of the raspa juice in what we all call the catch cup changing? All right. So here's what the stand looked like. It was a very primitive stand. It had like a little counter, and it had like a little window, and there was like a pallet sitting down here that you could stand on, and the roof was like this, and then here was the window, here was the guy that sold them. This was the screen, and right here there was a little stack of catch cups that you could take, right? And the catch cups, I know you've seen them because they're the paper condiment cups that you like pump your ketchup into. They're made of paper, and they have these pleats in them like this. And when you're done, you can like open up the pleats and lay them flat, right? They're made by like the Dixie company, right?
They're at Freddy's.
Oh, they are? Okay. They're real cheap and inexpensive as well. So yeah, you just pull the pleats and lay it flat. Okay. So what I did is I'm like, okay, I'm smarter. I'm smart now, or my mom got mad at me after several times where I did not get the catch cup. So I'm saying, okay, mom. All right, mom, I'll get the catch cup. So I still got to move out of the way. Okay, so there it is. And now this arm is longer, and this arm is holding the catch cup. So no, don't draw, mom, because angry faces are hard to draw, right? Yeah. So anyway, here's the cylinder. I'm holding it now, and I guess I need to move over to catch it, right? Otherwise, I'll miss it. There I am. So let's break my arm and connect it again. Okay. So there it is. Now, the rate at which it's going into now, not my clothes, but the catch cup is +2. Yes. So C works nicely there. It's for clothes and catch cup. But now I'm smart. It's not getting on my clothes. So notice it says now, at that same moment, when the depth of the snow cone mixture is 3 inches, how fast is the height in the catch cup changing? So the catch cup is a cylinder. Here's the formula for the volume of a cylinder, a right circular cylinder. The volume of a cylinder is, of course, pi r squared h. Now, that's right off the formula chart. Let's go ahead and draw some mixture in here. Let's say that there's already some mixture in here. I've already been catching it, right? I'm smart. Let's go ahead and label our unknowns. It says that the catch cup has a 2-inch diameter. So what would the radius of the cup be? 1. Would I call it 1 or R for radius of a cup? 1. Okay, now look down here. What am I going to call the radius of the mixture? R? Or do I call it 1? There you go. That's the difference between a cylinder and a cone. A cylinder fills up all the way across, and the radius does not change. So don't call it a variable. But in a cone, it does. So that eliminates the need for a variable. Heck yeah. If you can have fewer variables, it's better. Now, I'm not going to call the height of the mixture. It doesn't matter how tall the cup is. Right now, it's tall enough to catch the drippings. But I can't call it H because I don't want to get confused with this H up here. So I'm going to use Y, because Y is another variable that we typically use for vertical measurement. Now I have to modify my formula off here to the side. That's right off a formula chart. I have to modify it for my variables. So instead of V, I'm using capital C. Instead of H, I'm using Y. And instead of R, I'm using what? 1. So the volume that is collecting on my into my catch cup now is pi times 1 squared times Y, which is basically pi Y. This is your position equation. If you know the depth in the catch cup, you can figure out the volume in the catch cup. If you know the volume of the catch cup, you can figure out the height of the fluid, the raspa mixture in the catch cup. I want to take the rate equation now, the derivative with respect to t, because what's my target? What did I say? I didn't give myself a target. How fast is the height changing? So what I'm looking for on this problem here now is I'm looking for dy dt. That's my target. So we'll take the derivative, and I get dc dt equals pi times 1 times the chain rule dy dt. And now I'll plug in when h equals 3. Notice there's no h in my equation. I'm still referencing that same moment way back up top. And now I plug in. dc dt is what type of 2? Positive or negative? Positive equals pi dy dt. And now I'll solve after I plug in dy dt is equal to 2 divided by pi, and now the units are going to be inches per what? Minute? Yeah. And it's a positive rate. So if you had to explain it again, you say when h equals 3 inches, comma, the height of the raspa mixture in the catch cup is increasing, or y is increasing by 2 pi inches each and every minute. Okay. So that's a really nice problem because you do change shapes. You change from a cone, which has a negative rate of change of volume, into a cylinder, which now has the same magnitude, but it becomes positive. So there are variations on this right here. I've been dealing with these types of problems my whole life because I graduated from conical raspas and cylindrical catch cups to every morning a coffee filter that decants into a pitcher on my automatic coffee maker when I make my own black silk Folgers coffee. Okay, and it's a cylindrical decanter, and it's a conical, if you will, basket, right? So it's kind of the same idea. So there are problems, and I think there's one on the worksheet where it's the same idea. You've got coffee percolating into a cylinder, and it's pretty much the same idea. It might ask you for different things, different scenarios, but that's it. That is the cone problem. And if you understand that, you're good, all right? Very important to find that auxiliary relationship. And if you can make it in terms of R or H before you take the derivative, that's the thing to remember. It saves a lot on the back end. An ounce of prevention worth a pound of cure, right? That's a 16-to-1 ratio. That's pretty good. All right. Any questions, comments on that one? All right. I'm going to skip this one here, but it's another cone problem. I'm going to go to the last one here. Example 11, because these show up quite a bit too. If you read this one at the beginning, it kind of sounds like the beginning of a Stephen King novel, right? Look at that. A young boy is out at night, comma. Ooh, spooky, right? What is he doing out at night? He should be home sleeping, or at least at home doing math. What is he doing? He's running. I'm running towards a street lamp. He's running towards a street lamp at 6 feet per second. Okay. If the street lamp is 30 feet tall and the boy is 5 feet tall in his jazz running stance, assuming that's a constant, he doesn't bob up and down. When he is 4 feet from the base of the lamppost, A, how fast is the length of his shadow changing? B, how fast is the tip of his shadow moving? Those, believe it or not, are different questions. Step one, draw a picture of a young boy out at night. Okay. Be careful how young you make him. I don't want you to get in trouble. Okay. Okay. So there's the street. Now I'm going to draw the street lamp. The street lamp, I'm just going to draw as a straight line. And what the heck? I'll put a bulb on it, right? I'll make it a pole. There you go. And is that, am I going to label that L for lamp or 30? 30. That doesn't change, right? That's 30 feet tall. The boy is going to be right here. I'm just going to draw the boy like this. Yep. Boom. And he's running in this direction. He's moving that direction towards the street lamp. And this right here is what? A constant or a variable? Do I call that height for height of the boy or 5? 5. We're assuming that's a constant. Okay. Now I need to label some other parts. So how am I going to draw this? Well, this is how light works, everybody, if you were curious. Yes. Because here's how the light will work, right? If you want, and you could, again, this is nice to be able to do with Notability. The light is going to illuminate everything in front of it, right? Everything behind it, everything above it. Okay. Except it's not going to land behind the boy, right? On the ground. That is where he blocks it. Boy, quit blocking your shadow. This then is the shadow. And what do you want to call that? S for shadow? You can. But look, my S's look a lot like my 5s. And I don't want to get it confused. So I typically use like a lower script cursive S for shadow. I want it to be meaningful. The shadow. Now I want to label this. This is how far away he is from the lamppost. That also varies as he's running towards it. So it needs to be a variable. What do you want to call it? D for distance. Okay, nice. Way to contribute. Nice. Now we've got 30 and 5. Do we need to label the hypotenuse? Because we'll assume that this lamp is at a right angle. No. We'll assume he's running at a right angle. No. All right. So now let's go ahead and label the rates. We know 6 feet per second is how fast he's running. So I'm not going to use D for distance because we use the derivative D. I'm going to use X. Or you can use big D if you want. Small d is a bad one to use. So if he's running towards the lamp at 6 feet per second, is that dx dt or ds dt or what? Something else? If he's running towards the street lamp, which variable is that immediately affecting? X, good. So that is dx dt. We label our rates. Now, is that a positive or a negative number? X is from the base of the lamppost to the base of his feet. Yeah. It's getting smaller. Yeah. X is decreasing. If he were running away from the lamppost, that would be a positive rate. Okay. So we got that labeled. What else? Is there any other numbers up here? Street lamps 30 and 5. We got that. When he's 4 feet from the base of the lamppost. So here's even creepier. When X equals 4, someone takes a picture of him. Yikes. That's the snapshot moment. Okay, perhaps, right? Now we can create our target on part A. How fast is his shadow length changing? So that's d what dt? ds dt. There's our target. Okay, good. So if you set up related rate problems this way every time, it's going to make everything go so much smoothly, so much more smoothly. All right, so I got dx dt and I want to find ds dt. Those are the two rates I want to relate to each other. But before I can relate their rates, I have to relate their quantities. So how am I going to relate x to s in this diagram? Similar triangles. Good. We can't use the Pythagorean theorem because there's two different triangles. But what was the secondary equation for the previous problem becomes our primary equation. Yeah. So we can say x plus s. It doesn't matter. X plus s, the big base across the bottom is 230, the big height. As little s, the base of the small triangle is 25, right? You could do it that way. Or you could say corresponding ports. 30 is to 5. That's the big vert to the little vert. As the big horizontal, x plus s, is to the little horizontal s. It doesn't matter. Your cross products are going to be the same. Now, I think the second way is a little bit easier in this case because 30 divided by 5 simplifies, doesn't it? So I'm going to stick with this one here. I'm going to call this 6 equals x plus s over s. And there's my primary equation. But you know what? Can we simplify it even more? Yeah, I'm going to multiply both sides by s. So I get 6s equals x plus s. And then I can combine like terms, right? Subtract an s. So I get 5s equals x. And that's about as simplified as it can get. So now we can say x equals 5s. Or if we need it, we could say s is equal to 1/5 x. And again, just like in the previous problem, that not only relates the two quantities to each other, if you know one, you know the other, but if you need to relate their rates, you could differentiate that. dx dt is 5 times ds dt, and ds dt is 1/5 of dx dt. Okay, so that's my primary equation. Now, which one of those am I going to use? Well, let's come over here. What's our target? ds dt. So I might as well use the one that's already solved for s, yeah? So here we go. d dt, boom, boom. We get the derivative of the left is ds dt. And on the right, we get 1/5 times the derivative of x, which is 1, times the chain rule dx dt. There's your rate equation. Now notice there is no x variable in it, is there? So it turns out that the rate of change of his shadow has nothing to do with how far away he is from the base of the lamppost. It's only a function of how fast he's running. In other words, it changes at a constant rate. But we'll still reference that moment when x equals 4 colon, we get ds dt equals 1/5 of dx dt, which we labeled as -6. And if I simplify, that's -6/5, and then you can write it as feet per second. Or if you want to make it meaningful, that's the same as -1.2 feet per second. So when the boy is 4 feet from the base of the lamppost running towards it, his shadow length is decreasing by 1.2 feet each second. Yeah? The shadow length is getting smaller. That's how you would write that sentence. I'm not going to write the sentence. All right, so that's part A. Part B, how fast is the tip of his shadow moving? Well, the tip of his shadow is right there. I want to figure out how fast that tip of the shadow is moving that direction. So let's give myself a target. I'm looking for d what dt for the tip of his shadow. Is it just ds dt? It can't be just ds dt because that's how fast the shadow length is changing.
Yes. Oh no.
Well, is a variable that I want to look for the change in even there? Let's think about this. If he is moving towards the lamppost at 6 feet per second, then his feet are moving at a rate that's dx dt. I just want to say how fast is that point a little further back moving towards the lamppost. So I really want to know how fast is this entire length changing. Got it? I don't need to introduce another variable for that because I can build it up. It's just x plus s. Yeah. I want to know how fast that whole distance is changing. So there's my target, dx plus s dt. Now, how in the heck am I going to evaluate that? This one's a little bit different because what I'm going to do, since it's already a derivative, is I'm just going to kick that out of the numerator and write it like this. That's essentially what we do when we take the derivative of y with respect to t. We just slide the y into the top and ddt of y becomes dy dt. You can do the same thing in reverse. And now I could take the derivative of each term. That's dx dt plus ds dt. We had that property. Okay, we had that property that says you can take the derivative separately. So now we're ready to plug in. Okay, when x equals 4, colon, dx plus s dt, I'll just rewrite that original expression, is dx dt. Dx dt was given, right? It was -6 plus ds dt, which didn't we just find that? That was -1.2, which if you combine those is -7.2 feet per second. And again, notice this is all at a constant rate. Doesn't matter how far away he is from the lamppost, assuming it's still casting a shadow. It's just a function of how fast he's running. So when he's 4 feet from the base of the lamppost, he's running to the lamppost at 6 feet per second, but the tip of his shadow is running towards the lamppost at 7.2 feet per second. And now I think it's pretty obvious exactly from what this young boy is running. He's running from himself. He's running from the tip of his shadow, apparently. And will the tip of the shadow get him? Yes. The tip of his shadow is going to get him because it's moving faster than he is. In fact, the tip of the shadow, I'm going to get you, I'm going to get you, is going to get him at the exact same time as the lamppost gets him. Oh, no. We should drop our camera and say, young boy who's out at night running towards a lamppost, stop, turn around, go home. Don't be afraid of your own shadow. Right? But there you go. That's how you do those problems. Okay? It's similar triangles. The second one, you already have the information. You're just adding them together, which makes sense. It's the sum of the two. Okay? And we are now done with related rates. Yay, which means we're now done with officially, for now, the first half of the House of Calculus. We're going to come back and make improvements later on, but starting tomorrow, we're going to start building on that second half of the slab. So the 5 problems are due tomorrow by 4:30 p.m. And then your next set of 5, they're in, I put a new link in Canvas and they're in AP Classroom. Yeah. AM. Yeah, it's open right now. Yeah, they'll open at 4:30 the morning of, and they're due 4:30 the next day. So it's 36 hours. Yeah.
Well, work, how do we get it to?
Work. You do it in Notability and you submit it to that folder. I'm always going to put a link that's an assignment link to AP Classroom, and there'll be a tray that you could submit your work to. And you can take pictures of it if you do it on paper and upload them in a Notability, or just upload your Notability because you're doing your scratch work directly in there. Okay, that's all right. 5 questions. It's pretty manageable. The questions that are in tonight's 5 questions are a little bit more straightforward. It's not so much computing. It's basically, do you understand how to set them up? Do you know how to relate your variables and then relate your rates? And then the next set that I'll assign on Thursday, there'll be a cone problem in there for sure. And, you know, maybe a sphere is increasing or something, or boys running out at night or walking towards the lamppost. So those would be more computational. Again, the worksheet's out there. The keys to the worksheets are out there. So at this point, how badly do you want it? You can practice, practice, practice. And then Landon said that we're going to do reviews next week, not this week, maybe Tuesday, maybe Thursday, maybe both. So if you came to that first one, I hope you found it helpful. It's really nice that he's doing that. Yeah, Tuesday and Thursday during 7th period. So anyway, take advantage of that. We will get to the end in class. We're just going to move quickly. Okay. I'll give you all the info that you need, but I can't practice for you. I'm here every morning though. Every single morning I'm here. I don't have a morning duty ever. Nope. I just have an afternoon duty. Unless I eat bad chicken like Ethan. No, Ethan, that looks actually pretty good. Yeah. The chicken I ate was not like that. Then I'm not here in the morning. Okay.